Hi and welcome everybody to the 14th lecture on wireless communication course. In today's lecture, we will be talking about techniques for overcoming interference in wireless systems. In the previous lecture, we talked about diversity techniques and adaptive modulation schemes and MIMO methods that can enable us to overcome the fading in wireless channel. Now, in this lecture, we'll try to look at a different obstacle that exists in the channel, which is inter-symbol interference or self-interference, we call it sometimes, and they try to learn and study the techniques that can mitigate this type of interference. So the outline of the lecture is going to be as follows. First, we will discuss and look at the inter-symbol interference countermeasures, the main enabling methods that can avoid inter-symbol interference. First, equalization, then multicarrier waveforms. After that, we discuss spread spectrum and how it can reduce the inter-symbol interference, and then talk about directional antenna techniques and massive MIMO systems that can enable to mitigate it as well. Then we move to discussing these things in details. OFDM waveforms, then spread spectrum, both types, direct sequence and frequency hopping spread spectrum. And then we talk about the interference rejection in direct sequence spread spectrum and the rack receiver in CDMA. Then we also explain multi-user systems, the downlink and uplink channels, multi-access techniques and random access techniques. But before we start with the lecture, I would like to go over the following questions that I expect you to be able to answer by the end of this lecture. Regarding fading, interference, Doppler, and delay spread, in general, small-scale fading. So the first question says, would you like flat fading or dispersive channel? Which one is better and why? Or it depends. Is time variation of channel desired or not? How to handle delay spread? If you have delay spread in your channel and affects your data, how to handle it? How to handle Doppler spread? How to handle interference? Delay spread and Doppler spread cause interference. How to handle the interference resulting from them? We have many different types of interference, but for now, we will discuss the self-interference, which is your interference, called inter-symbol interference and inter-carrier interference. This is from the design, the system design, and co-channel interference and adjacent channel interference, which are coming from others. Co-channel interference means you have another signal coming on top of your signal. Co-channel interference. That's not desired to you, it's for another user. Adjacent channel interference coming from the adjacent bands due to dispersion in the channel or the filter you are using at the transmitter or something. So these questions altogether motivate us to find techniques and methods to resolve the above issues. So this is what we will be studying in this lecture, the techniques and methods that can mitigate these types of interference. So the countermeasures for inter-symbol interference are listed as follows. First, we have the equalization. Equalization means you try to remove the effect of your channel on the data. Try to remove the effect of delay spread. Try to remove the effect of Doppler spread. Try to remove the effect of fading on your data, the desired data for yourself. For that, we use signal processing at the receiver to eliminate inter-symbol interference. It's complex at high data rates. The equalizer, we can use it up to certain data rate at the receiver, especially in time domain. Now, if you want to build high data rate transmission systems, then what's the problem with high data rate? Anybody remembers? When you transmit your data rate with high data rate, the symbol duration shrinks because the bandwidth is large, symbol duration shrinks. So it becomes the delay spread of the channel usually becomes much larger than the symbol duration. And when the delay spread is much larger than the symbol duration, you end up having multi-path channel of X number of taps. Now, more taps you have, more difficult your equalizer becomes. It becomes really complex. So this is why data rate, when you want to increase your data rate, you increase your data rate by increasing the bandwidth of your symbol. But this results in reducing the symbol duration. Reducing symbol duration compared to the delay spread becomes problematic for equalization. That's why it's really this very complex, and we used it just in we used this in 2G and 3G. After that, in 4G, we stopped using these types of equalizers, and we just use new types of equalization that are performed in the frequency domain, where they are much easier. So after that, another technique that helps us to remove the intersymbol interference is the multicarrier modulation. This is coming to address the equalization problem in time domain. I told you equalization here is very difficult in time domain. This in OFDM, for example, which is orthogonal frequency division multiplexing modulation, an example on multi-carrier modulation, is using frequency domain equalization. In time domain, the equalization is very difficult, very complex, but when you move to the frequency domain, it becomes easier, and you can recover your data with less complexity. So in this, the concept here is to break your data stream into low rate substreams. So you have large bandwidth, you divide it into sub bandwidths, and these small bandwidth now represent what? Large symbol. Large symbol, the delay spread within the large symbol, so does not get affected by that. This is the trick they use. Now we have another also technology that can help reduce the symbol interference called the spread spectrum. And this spread spectrum, you take your data rate, which is relatively sometimes low, and you multiply it by a chip sequence that has high data rate, then your signal spreads. So the signal level becomes under the noise level, so it becomes robust against interference, robust against multipath interference as well, and you can recover your data easier, especially with the fact that when you use high speed chip sequences, you can resolve the multipath components in a much easier way, and resolving these multipath components, you can exploit them for multipath diversity and enhance your bit error rate. Antenna techniques like massive MIMO. When we have, for example, directional antennas means they are not transmitting in all the direction. When you have directional antennas, your signal is limited within the beam. So it does not go back and hit by the building and go to the receiver. So your delay spread automatically reduces. If your delay spread reduces, the intersymbol interference between the adjacent symbol reduces. Everybody knows that we have these symbols, we are transmitting them, packets or symbols, whatever. The problem when you transmit it, we transmit back-to-back symbols, yes? When we transmit them over the channel, due to the channel, we get interference. So this is the interference due to the channel. Since we have another packet that's back-to-back here, this affects the data on the adjacent packet. We don't want this to happen. To avoid this, we usually sometimes put guard bands, guard times or guard periods where the interference goes within this guard. It's like kind of a protector, protects you against the intersymbol interference. And this is usually with multi-carrier modulation. Here, no. You take this combined with the packet and you try to cancel it intelligently by complex equalizers. Spread spectrum has a different way to do that. Antenna techniques try to reduce this to very, short delay spread so that you don't get affected too much. So equalization, let's have a look and understand what's equalization. Equalization, as we said, it compensates for the effect of the channel, and most importantly for the effect of intersymbol interference created by multipath time dispersion channel. Equalizers are usually adaptive to the channel. You need to update them frequently. As the channel changes, you need to update them. Because the channel is usually unknown and time varying, it varies continuously, and equalizers have to track the time variation and adapt according to the channel behavior. Equalizers in most of the time are implemented on the baseband, not passband, baseband after the carrier modulation. And there are two-step approach to perform equalization. First, you need to do training to learn the channel. Training is the process that the transmitter and receiver learn the channel between them. Why do you need to learn the channel? To know, if you don't know the channel, how are you going to handle the intersymbol interference? It's difficult if you don't know the channel model. But if you know the channel, then you know the delay spread, you know how many taps, then you can design your equalizer in such a way that has these many taps so that you can remove the effect of intersymbol interference. So training, how training works, the transmitter sends a known sequence to the receiver. The receiver knows this sequence, so takes the received sequence and divide it by the known sequence. By doing so, what do you get? You get the response of the channel on the sequence. Simple, like this. Now, once you take the channel, you learn from the channel what's the delay spread, how many taps, this and that, and you design your equalizer by making use of this information. Tracking the equalizer, it tracks the channel changes with the help of the training sequence and uses a channel estimate to compensate for distortion. Now, as time goes, the channel will become different. So you need to adjust these channel parameters that you stored at the receiver side so that you don't equalize your data with the old channel version. You equalize it with the updated version, with the current version, because if you do that, you lose your data because that was not the channel experienced by the data. Now you have a new channel. So tracking is very important. Also, channel prediction is very important. Instead of keep training and sending signals to estimate the channel, you predict the signal ahead of the time. Before the channel changes, you know how would the channel will be after 10 seconds. This is very useful because it reduces your overhead. Equalizers can be classified into two types, linear and non-linear. Linear, the system model of the equalizer follows a linear model. And in linear equalizers, the previous detected symbols are not involved in the equalization process. So you detect instantly. And whatever you detect before, like in the past, it's finished. You don't involve it in the detection of the coming symbols. Example on these are zero forcing and minimum mean square error estimator. These are sensitive to spectral nulls in the channel responses. Spectral nulls are the cases where you have deep fades in the frequency domain. So it becomes like null, zero almost. Never zero actually, but when the value is so small, you approximate it to zero because if you divide by it, the power will go to infinity, which is impractical. And it causes noise enhancement problem. Noise enhancement, why noise enhancement happens? Because your channel, what do you transmit? For example, this is your data X, and you transmit it over the channel, you multiply by H, and then at the receiver, noise is added to it, yes? And this we call it Y, the received signal. Now you need to equalize. The easiest and simplest way to equalize your channel if it is single tap is to divide by H. What's my goal here? My goal is to know what's X. If I were to know what's X, I would need to know N, H, and remove them to get X. But in practical situation, we can never know what's the noise. That's why we are contradicting the math here. If you were to know X in math, regardless of N and what N and H are. What would you do? First you will subtract, then you will divide. But in wireless communication, in communication system, we do the opposite of mathematical science definitions. We are dividing and not subtracting because we don't know the noise. You can never know what's the noise. You can estimate the channel, but you cannot estimate the noise. The noise is random and coming on your receiver when you receive your data. So you divide by H. Now when you divide by H, H with H goes. So what do you have here left? X plus N over H. Now N is noise over H. You enhance your noise by H. Suppose that the H value here is small, like null, deep fade. What happens to the noise signal? Goes exactly reaches very high values. It affects your symbol. The noise overcomes your signal because you amplifies it. So this is the problem of noise enhancement. And you got it why we divide by H, we cannot subtract. That's really a problem in wireless. And this why? Because nature like this. You can know H, but you cannot know N, which is the noise. And your goal is to know X. So our communication systems are always limited by noise. And channel, we can, all the techniques and most of the techniques we are developing in wireless to overcome the effect of channel. Try. And the coding science is to reduce the effect of noise. This is the communication problem. Try to send your data from the transmitter to the receiver successfully. So to do that, you need to remove the effect of noise and H as much as possible. Now, nonlinear equalizers, these equalizers depend on the previously detected symbols, not only on the current one. Example on these, decision feedback equalizer and maximum likelihood sequence estimator. So these are the two equalizers that we use. Now, let's understand these equalizers more. Zero forcing. As we said, zero forcing, it tries to force the channel interference to zero. Intersymbol interference is forced to zero at all instances except k equals 0. Why k equals 0? Because we don't have interference at k equals 0 the time you receive. This is your desired data. You have interference after k equals 0 due to the spread of the channel, where the symbol of interest is assumed to occur. This is at k equals 0. It ignores the effect of noise and leads to noise enhancement. It ignores this problem actually. It just divides by H and does not care about N, what will happen to N. One of the solutions for this problem is to avoid the deep fade channels. Don't equalize when you have deep fade. Even don't transmit over them. Now, the second equalizer is minimum mean square error, minimum mean square estimator. And this reduces the effect of both channel noise and intersymbol interference. It tries to balance between try to remove interference, but also try to avoid enhancing the noise as much as you can. So it kind of strike a balance between both. Works better than zero forcing, but still it's not the optimal one to do. Decision feedback equalizer, which is nonlinear, consists of feedback filter and feed-forward filter. This is feed-forward filter and this is feedback filter. Feed-forward filter, it tries to collect all signal energy on the main tab, which is the tab at which you have your desired symbol, while suppressing the interference from subsequent symbols. The feedback filter removes the intersymbol interference from previous symbols. So two processes running simultaneously. One tries to collect the energy of the desired signal, and one tries to remove the inter-symbol interference from previous symbols. The second equalizer, nonlinear equalizer, is maximum likelihood sequence estimator. This maximum likelihood sequence estimator is one of the most complex equalizers you can ever design. But if it's the most complex, then why do you use it? Because it's also the most optimal equalizers you can ever have. How does it work? Look, remember with me the channel model, this y equal hx plus n. This equalizer, it tries to take y, yes, and then h, x. The receiver knows h and knows y because he receives y. The receiver takes y. And h, by training, he can get it, he can learn it. And then try to minimize the difference, this difference. What value of x I can put in this equation and give me the minimal value? So what's the value of x? What's x actually? X is the modulated symbol. So if you have 16 equam, how many different x's you have? 16 different x's. 16 because means 16 equam means 16 different symbols. If you have 128 equam, how many different x? 128. So to know the symbol that's closest to your received data, how many for loop you want to do? Or you have to do actually 128. 128 times you execute this for loop and get the result, and then after that you calculate what was the minimal value. The minimal value you get, you go back and say the symbol that corresponds to this index is the symbol that was transmitted. Got it? The metric, this is like the distance, how far this hx from the receive. Do you include the noise? You don't include the noise. So the effect of the noise is still there because you cannot include the noise because you don't know the noise. But you got it how it works. The metric values are formed for different symbol sequence hypotheses. The sequence corresponding, the sequence means the sequence or the symbol corresponding to the largest metric, whatever that metric. In the case I explained just now, I used the distance metric, square difference and square it. The largest metric determines the detected sequence, indicating how well the model of the received data fits the actual received data. So it's like kind of trial and error. You try all the possible cases, and the one that gives you the optimal result, you take it and say this was the transmitted symbol. In practice, a brute force search of all possible sequences would require high computational complexity. Obviously, I mean, it's not direct estimation, yes? So these are the 4 common types of equalizers that we usually use when we are utilizing single carrier modulation schemes, not multi-carrier. Now, as another solution for inter-symbol interference to avoid this complexity in equalization, we try to design the transmitter and receiver in such a way that we can transmit our data with much higher speeds while also reducing the complexity significantly. How do we do that? You want to transmit 10 gigabyte, yes? If you transmit 10 gigabits per second with this with single carrier, you would end up having an equalizers of maybe 100 taps. So it's really complex because the complexity of the maximum likelihood estimator increases with the number of taps and also number of different message symbols you are transmitting. So how does multi-carrier modulation simplifies equalization and make it possible to receive your data in a much easier way? You take your database, your data rate, and you convert it from serial to parallel. Yes, this, let's agree on this. This R represents the data rate. And if you were to transmit it directly to the channel without multi-carrier modulation, you would need complex equalizers. Why? Because this R has short symbolic duration but large bandwidth. As R increases the data rate, more bandwidth you need, yes? So this short symbolic duration, when you pass it through multi-path channel, what happens? The delay spread is much larger than this symbolic duration. The delay spread is this, and the symbolic duration is this. How many taps you need? The duration of the delay spread over the symbolic duration. You may have, when you have large amount of data with high speed you want to send it, you may have 100 taps. So this is really complex. You would wait 1 minute or half minute to get your data because of the complex equalizer. It does not make sense. And this limits our data speed. We want high speed, fast internet. With the previous techniques, we cannot achieve that. With this technique, the beauty of this technique can allow you to do that, can allow you to watch video, can allow you to do real-time gaming, augmented reality, virtual reality, streaming, this and that. See, these applications are enabled by physical layer techniques. Without these techniques, we would not have YouTube. Never, ever. It's difficult. We would not have streaming and these. These solutions are very, I know they are not known to the people too, but these are the fundamental technologies that are carrying most of the applications. So what do? We divide this into chunks, small data bits. Like you divide this R into n number of subcarriers or substreams. And each one, R over n now, becomes small. Now small data rate, smaller bandwidth, larger simple period. Larger simple period, when you send it through the channel, the delay spread will be within the simple period. So instead of having this simple period, here you have this simple period. So the channel is within. So you don't have this, you try to avoid this delay spread. This is how you avoid the delay spread between the symbols within the packet, within one block of OFDM. But how do you avoid the interference between adjacent OFDM? We put guards. So here, after you have your data here, you pass it through modulator, equal modulator, let's say 64, and then you multiply by carrier. This carrier determines at which frequency this data symbol will be carried. At the baseband. Is that
the transmitting part, right?
This is the transmitter part, yes. And then you sum all of these signals and put them on top of each other. Now one might say, how come you are summing and putting on top of each other? You told us when the signals come on top of each other, they cause interference. I tell you, they don't cause interference because the cosines here are orthogonal to each other because of having different frequencies. F0, F1, F2, F3. In the time domain, they look like interfering with each other. But when you move to the frequency domain, they get separated. In the time domain, looks like this. You have this first signal, this second signal, this third signal, this fourth signal. It's mess. It's really critical interference. You don't know how to handle it. But when you take the Fourier transform of this signal, you get the first signal here in frequency, the second signal here, the third signal here. So they are separated, not interfering. This is the magic of transforming from time to frequency. The old equalizers, they were trying to equalize and remove the effect of the channel by focusing on the time domain. In the time domain, you cannot do much. It becomes complex and more complex as the number of taps increases. So here the trick, you go to the frequency domain. They are interfering on top of each other with this method, but when you go to the frequency domain, they are nicely separated. You just synchronize to each one and get your data from it. So the main thing to know here, you break your data into n substreams. These n substreams, they have low data rate, but altogether they have large data rate. Substream modulated into separate carriers. Substream passband bandwidth is B over N. This is the bandwidth of your one subcarrier. And the total bandwidth of all the subcarriers is B. So now when you divide over N, this B over N becomes less than the coherence bandwidth of the channel. What does this mean, less than the coherence bandwidth of the channel? This means that each subcarrier experience not frequency selective channel, but flat fading channel, which you can equalize it by simple division over the channel value. If it was frequency selective, then we didn't solve the problem of equalization. Flat fading, very easy to equalize, just division, not complex filters, forward, backward, sequence estimators, maximum likelihood, just division, one like dot-wise product, or sometimes point-wise product, just each value with the corresponding one. This is the least complex process you can have in equalization. And accordingly, you will not have any intersymbol interference. So this is only handling the intersymbol interference. As you can see, we are not talking about Doppler. Doppler will create intercarrier interference. Interference not in time domain, interference in the frequency domain. These carriers will start smearing and spreading to the other adjacent subcarriers. This is very problematic problem. Very disastrous thing to happen in OFDM. If it happens, your system collapses. You cannot detect your system. That's why OFDM is very sensitive to mobility. You need complex techniques to handle it. So OFDM is robust against intersymbol interference or time dispersion, but it's not robust against mobility, Doppler. It's very sensitive to it. Overlap, we can have completely separate subbandwidth. These are the things that I explained. OFDM overlap substream. The other one feature that you need to care about when you talk about OFDM is the fact that OFDM enables you to put the subcarriers in a way that they are overlapping with each other, but still you can still detect them separately. For example, in the old system, if we want to send 3 symbols, we used to put the first symbol in the first pulse or carrier, the second on the third on the third carrier. So they are not overlapping. We said that if they overlap, they cause interference, and we don't want that to happen. In OFDM, the carrier, they overlap them, and still they don't have interference. How come? They tell the basic idea behind that is that to detect your symbol, you don't care about these points. You only care about the symbol at the peak, because these are all carrying the same version of the symbol. So if you can detect this with zero interference from the others, see here, the contribution of this to this point, 0, starting from 0. Then you can get your data without any interference. So instead of using 2B, double the bandwidth to transmit 2n number of bits, you are using just B. That's the overlapping. You overlap but don't cause interference. So overlapping subcarriers and FFT implementation. Now OFDM is usually implemented by using IFFT operation. What's IFFT? IFFT basically is a matrix, like the ones who know image processing and this, you have cosine transform, discrete cosine transform, and this. IFFT is similar to that, but it's complex, in the complex domain. You have here one column, second column, third column. These columns are basis function, exponential of something. Let's take the first column. The first column is exponential of, let's say, e to minus j 2 by fct. This exponentially from math, it equals to, from Euler identity, cosine, yes, cosine 2 pi fct minus sine. So if from this exponential, if you plot this in time domain, the real part, you will get cosine. If you plot the imaginary part, you will get sine. And this basically exponential function depends on the frequency points. So your cosine and sine that I showed you here, instead of multiplying separately your substreams, when you use IFFT does that implicitly. Yes, they are built in. The cosine and sine, they are built in. They are embedded. You don't see them. It's nice implementation. So this takes the real value of your symbol and gets multiplied by cosine, and this takes the imaginary value. So basically, IFFT for any complex symbol, IFFT for, let's say, real plus imaginary m, is equal to the IFFT of real plus IFFT of imaginary. Yes? IFFT of real is the cosine, and IFFT of the other part is the sine. So you sum them on top of each other because sine and cosine are orthogonal, they don't cause interference. So this is what all these, we call them basis function. What's the difference between the first column and second column? The only difference is if. Here if not, if1, if2, if3, if until fn. And these are adjacent to each other. So this basically, the math here goes to signal processing, and this goes to communication system. Multicarrier modulation splits high rate data stream into lower rate flat fading substreams. Overlapping subcarriers reduces bandwidth by factor of 2, and we showed you how this can happen. Modulate symbols with IFFT at the transmitter, the way I explained here. This is how it works. Actually, you can really understand this deeply when you go to MATLAB and build IFFT by yourself and try plotting the real part and the imaginary part and see how the cosine is coming and sine is coming. And the sink also. The sink is the Fourier transform of this, of the cosine. Well, sink is coming from where? Sink is coming because this cosine and sine, you cannot allow it to go for infinity. It's limited by the duration of the vector, by the dimension of the vector. What's the dimension of the vector? In points. Let's say each point is 0.1 millisecond. Then n multiplied the duration of this. And what's this? The duration of something. It's like rect over cosine. You take cosine within a duration, you truncate it. Now truncating this rect in time, when you transform it to frequency, when you go to frequency, transfer it, you get sink. Rect is sink. And these f values, they shift the sink at different frequencies. This is what happens from the where rect is coming, from where sink is coming, where is cosine, where is sine, all of them here. So if you want to tell me what's OFDM, OFDM is IFFT. OFDM, the magic of OFDM is all happening in the IFFT. And what's the sad thing about that? When you go to MATLAB to implement OFDM, MATLAB gives you IFFT as a ready function. You don't know what's going here. The science is hidden from you. You don't know. You just take your data here and you get output data here. You don't know what's the relationship between this point and this symbol. The data before IFFT, we call them symbols. These are the modulated QAM symbols. But after that, we call them samples. Each point sample here is coming from the contributions of all the symbols. From all the symbols. And how does this happen? By this basis function, cosine and sine. It's really, this is what's OFDM, the I50. If you were to produce or innovate or contribute a new thing to OFDM, you must understand this block very well. And here where you can do this. I really, that was something that I enjoyed during my studies. I used to look at MATLAB, and always MATLAB gives you the I50 ready. You can never develop anything new if you use ready function. You must go inside that function and see how it works, and try to come up with a function that works better than this. After that, what do? You add cyclic prefix. Why do we need cyclic prefix? To avoid the interference between adjacent symbols, adjacent OFDM. This gives you vector, yes? But I want this, and there is another one coming. I want to put here guards so that I avoid the interference. And then after that, you take it to digital to analog. Here your data is digital, you transmit analog. You convert it, and then you multiply by the carrier frequency, FC. FC is your carrier frequency. When you say that my phone is working at 2.4 gigahertz, this is FC, not F of the I50. FC. The F of the I50 around 0, like F0 from 0 frequency, F1 from 0 frequency. That's why we call the process here baseband, here passband. And then after that, you transmit it over the channel that most probably is gonna be time dispersive, and then when it reaches the receiver, noise will be added, and so on. Cyclic prefix basically it eliminates your interference, yes, avoids but actually you cannot do that if you didn't have, like, what do we call it? We add cyclic prefix to be able to convert the convolution in time domain to multiplication in the frequency domain. Which is easier, convolution or multiplication? Multiplication. So when you have multiplication, what do you get? You are able now to do what? See, this model is in the frequency domain. When you get these multiplied with each other, how do you get rid of H? Just simple division. But if it was convolution, it's really difficult to do inverse convolution. The integration and this very complicated process. So CB, when you add it, your linear convolution goes to circular convolution. When you have circular convolution, the convolution can be transformed to multiplication in the frequency domain. And here, at this point, you can do your equalization. After A50. After A50, because I'm looking from this side, your data is coming from this side. This, you remove cyclic prefix, here you are still in time. You take A50, A50 is the opposite of I50. All the things that I talked about I50, they are coming here again in this. So, and then you take your data points in frequency domain, you divide by the channel, all of them, and you get your X, what you transmitted. So this is basically when you want to simulate OFDM, you have your data points. Yes, these are the bits. You perform channel encoding. Channel encoding increase your data bits length so that you become more robust to channel noise. and then you perform modulation, map bits to symbols on the constellation diagram. This is the constellation diagram that I showed you before. This corresponds to 4QAM or QBSK. And then you pass it to I50 process. After the I50 process, the magic I showed you before, in the I50, the output here is this signal. In frequency domain, this is what you see in the spectrum analyzer. And in time domain, this is what you see. This is the real part, and this is the imaginary part. And then you add guard interval. What's I and the Q? I and the Q, the in phase and the quadrature phase. You add I and the Q, and now you have this in time domain. You have your data, and this is the CP part. And we call this whole as one OFDM symbol. And you transmit it over the channel. The channel is this, dispersive. And then at the receiver you have guard interval. You remove the guard interval, assuming you have perfect time synchronization. Then you have FFT operation. After that, equalization. Here we call frequency equalization, FE. After FFT, and then symbol demapping. The symbols, you demap them to bits, and after that decoding and interleaving. This is basically what you need to do to simulate your system.
We can be at the noise.
The noise here at the receiver side here.
Well,
Here.
after the receiver.
Before at the receiver side, before you do any processing. Now, in spite of the many benefits, many advantages that we have mentioned about OFDM, but any benefit that you produce or introduce comes with usually some trade-offs. Let's look at some of the trade-offs that OFDM makes, or the design issues that are related to OFDM. First, OFDM suffers from timing and the frequency offset, because this impacts the orthogonality between the subcarriers, and we call this self-interference. Everybody remembers with me the carriers of OFDM? They are orthogonal to each other. Now, any misalignment, any slight deviation from here, any slight deviation, whatever small it is, it kills your orthogonality. You know what it means, it kills your orthogonality? The bit error rate will become extremely bad. So this means that you must ensure perfect synchronization, no frequency offset, no timing offset, to get your data successfully. This is the first problem. So it's sensitive to Doppler and anything that causes frequency offset. The second point, it's sensitive to peak to average power ratio. What's peak to average power ratio? Go back here. See this, the OFDM signal in time domain? After you take the I50, your input signal can be like this, uniform. The samples. After you take I50, your signal starts fluctuating randomly like this. Now this is very bad for the power amplifier, because the power amplifier usually operates on certain point and they try to avoid the saturation point. Suppose you are operating, this is the saturation point of power amplifier, this is the response of power amplifier, and you are operating here, yes? So your signal, this comes into the power amplifier takes it as input and it tries to amplify it. Now what happens here when the amplifier amplifies the signal? It will exceed the saturation point. If it exceeds the saturation point, what will happen to these peaks? They will be cut. What does cutting mean? Your data goes away. Your data, you are cutting your data, you are distorting your data before you transmit it. Very bad. And this cutting not only cuts your data and reduces your bit or rate, but also this cutting causes severe adjacent channel interference. This will smear like this, because you will you will cause intermodulation products in new frequency components, and this will interfere with the other adjacent OFDM symbols. Very bad, so we try to avoid these peak values. If we avoid them, then we increase the dynamic range of our amplifier. We have more freedom. Actually, I don't exaggerate that there are more than around thousands of papers to address this problem, the peak to average power ratio problem. Of course, the goal here is to come up with a technique, but also low complexity technique that does not increase your complexity so much. So you can solve this with the clipping or peak to average power ratio optimized coding or other methods. There are hundreds of methods available on the literature. Mitigation for fading across subcarriers. Now, although you avoid the intersymbol interference, but still you need to mitigate the fading coming on each subcarrier. To do that, you either use precoding, fading inversion, which is used in DSL, VDSL, and you try to avoid the deep fades by not transmitting over them. Also, another way to avoid deep fades is to use adaptive modulation, as I explained in the previous lecture. You make your data rate or the modulation order adaptive according to the channel situation. If you are in deep fade, what do? You use low order modulation like BBSK. If you are in good channel response, what do? You use high order modulation. You adjust according to the channel. Coding across subcarriers. Bits are encoded into a block code of length n for n subcarrier. Each coded symbol is sent on a different subcarrier. Coding is very important and critical if you want to improve your performance beyond the expected one. So this basically what OFDM is, the advantages, the disadvantages, how it works at the transmitter, how it works at the receiver, and the design issues that it has, and how it enables us to mitigate the interference and perform easy equalization at the receiver in the frequency domain, and help us send data rate with high speeds, which enables the use of high-speed internet. So we stop here and we continue discussing the other countermeasures for intersymbol interference in the next part of the lecture. Thank you very much.